Thank you very much for the introduction and for the opportunity to give a talk here. I'm very glad to be at this conference, and as the last speaker, it's my honor to propose that we give a generous round of applause to the organizers. Yes, we can. So thank you, Hannah, David, Kevin, and Jose for organizing an interesting and inclusive conference with so many excellent talks. I really loved it. Right. My talk is going to be about lifting rational points. I work on rational points, and this is going to be a quite general type of question that I'm going to propose to you. It's a recent work with Leo Herr, Sarah Mehidi, and Thibaut Poiret. The question that we're interested in is very simple. If we have a morphism f of varieties x to y over a field, okay, what is the set f of x of k as a subset of y of k? Okay, so I think okay, what do I mean? So x of k and y of k are the sets of rational points over k. These are points with k coordinates if you want, but also in algebraic geometric terms, they are just morphism from spec of k to x or to y. And I really want to know what is the image of the set of rational points. What can we say about this? Well, if f is surjective as a morphism of schemes and the field is algebraically closed, then these two sets are equal. And that is very easy. And we're all happy, and we can go home. But if f is surjective and the field is not algebraically closed, so then we don't necessarily have equality, and things can be actually quite difficult and go quite wild. So let's see. I'm going to probably write here. We are going to look at an example. The example is the running example of my talk. It's very simple. P1 to P1 over your favorite field, for example, the field of rational numbers. And I'm just going to take the map that squares the coordinates. And this is a nice projective map. And this is not surjective on Q points. Well, we all know rational numbers that are not squares, right? So this is our f. Why is it not surjective on Q points? Except for the number theoretic reasons that we know, or the properties of rational points that we know. What is going wrong here? So what happens is that this map has multiple fibers over 0, 1, and 1, 0. And this is the reason that prevents our surjectivity. So let's look at an example. So let's say that we have a point, and I'm going to make my life simple. I call my point with coordinates a, 1, and with an integer. This can be extended easily because P1 is projective proper to a map actually from spec Z. And I'm going to call this alpha. So I'm working over Z if you want to. What happens here? What happens is that I can look at this as a map here, but of course the composition is a Q point here or is at a point here as well. And then the question is what happens? What happens here? So what happens is that I can compute the pullback of, for example, 0, 1 as a divisor. And this is going to be, well, this one is 2 times 0, 1, right here, just because I'm taking squares. And then this 2 is going to be remembered. That is what makes my squares coordinates. And then if I look at the pullback here now down here, So I have a divisor, I pull back here, I have a divisor, and I pull back here. This is also a one-dimensional scheme, and I also have a divisor if there is non-zero, which is what I'm going to look at the generic case. And then this is sum over primes, so the divisor of the spec set, of 2 times the periodic valuation of A times the divisor corresponding to the prime P. And so this 2 is being remembered. So now, if I have just some random point from spec set to P1 here, for example, the point with coordinates 3, 1 or so, and if I look at the pullback of 0, 1, then I will not necessarily be seeing this. It will not be there. So that's why 3, 1 is not a point coming from P1 under this map. Okay. So this is to give you the intuition. We want to know which points lift. So we want to know which points that are Q points on P1 are actually images of some Q points on this other P1. And what we do, we can prove the following theorem. This is following ideas of Campana from geometry. And we can prove a first theorem which looks like this. So this is going to be like a general setting for the talk. So R is a Dedekind domain, for example, Z, and K is the fraction field. All right, and then I have X to Y, my morphism F, and I'm going to take it to be proper and surjective over K, and here Y and X and Y are, what do I ask, proper smooth. Varieties over K. And also, I will need to ask that F has some reasonable properties. So here I was telling you about multiplicities of fibers. I want that generically there is no multiplicity in the fibers. So the generic fiber is reduced. And then you see here, I have been working over Z. Because if I try to take pullback here, there's nothing interesting that I can see. So I will need to be working over R. And here I have varieties over K. So I'm going to take an integral model of Y. This is my Y tilde. And this is a proper R model of Y. And then, after we have all this setup, what we prove is that there exists up to removing finitely many points of spec R. So after excluding a finite set of places of my Dedekind domain, then I can sort of bound the image of the set of K points from X as some subset of the set of K points here that I can actually prescribe. So what does this look like? F of X of K, this is the thing that we want to understand, right? So this is going to be contained. The set of points, I call them betas. These are RS points, but because I chose my proper model to be proper, this is actually the same as Y of K, which is, of course, what I was. But I'm looking at them as points, RS points here, and S means I'm inverting this finite set of prime. I'm not going to write it down. Such that for every prime divisor, this is where Campana's theory comes into, D on Y, and for every, either beta lands in this divisor, and this can happen, and then I don't say anything about that, I will not be able to. Or if it doesn't land inside the divisor, then, well, I have something spec RS like here. This is a one-dimensional thing, so it might intersect the divisor without being contained inside. And then we see what happens at those intersections, which is essentially what happened in the example. And P of beta d tilde, the intersection of beta with the Zariski closure of my divisor d will be, well, the intersection can be empty, so the intersection multiplicity can be 0, or if it is not empty, then it will be at least as large as the minimum multiplicity of the fiber of f above d. I'm going to write this down, but I'm telling you a little bit what it is. And this is true for every prime of R which is not in S. So we have a possibly complicated looking set where d tilde and y tilde is the Zariski closure of D, and it is Cartier. So after removing a finite set of places, I can assume that my y tilde is regular, for example. So I can do this, or even smooth over R, because I started with something smooth. And this is only for the sake of exposition, because we can actually prove this statement without the smoothness assumption. But then the definition that I'm going to write down here are going to be much more complicated, and I don't want to go into it during a short talk. So we look at the pullback of this Zariski closure, and that is a sum over primes of something. And these are the intersection multiplicities, the coefficients of my divisor, and then we get P. So this is how I define this and P beta d tilde, these intersection multiplicities, or in the language of enumerative geometry, these are contact orders between the point and the divisor T, or the closure of T. And this MFT, which is the smallest multiplicity of a component of the fiber, so it is the smallest minimum over all possible components of the fiber of n dE, if n dE is the multiplicity of the fiber of the component E. So the pullback of T can be written as sum over prime divisors of X of n dE times E. So that's where it comes from. So if you want the formal definition, this is the formal definition. And because I chose my morphism to be to have reduced generic fiber for almost all divisors D, then this number is actually equal to 1. And so this condition is actually going to be trivial. So actually there's only finitely many divisors that give conditions. And these are the divisors that are involved in the construction of the orbifold base of the morphism F according to Campana. And this set here is also known as a set of Campana points on the orbifold base of the morphism. And the orbifold base is just a pair where we have Y, and we have this sum of divisors D, where these are encoded as multiplicity in terms of standard coefficients. I'm not going to get into it, but there is a connection with geometry there. So, okay, this can be a mouthful. It's a lot of new stuff. So let's look at our example. Oh, it's still here. That's fantastic. So according to the theorem, if we apply it to the example, what it tells me is that the image of the set of Q points is contained inside the set of points. I'm going to make some choices. I'm going to write them with coordinates A, B, such that I'm going to make a choice because it makes it easier for me to actually compute these numbers. These can be computed explicitly. So if A, B are coprime integers, then the condition given by this, well, we have only two divisors to look over. These are the points 0, 1 and 1, 0 for this map. And the first one gives the periodic valuation of A with this choice of coordinates must be either 0 or at least 2, because this for over those 2 points, this number is equal to 2. And then the same is for the other point that gives the same condition for B. So, and then of course, if we will land in the divisor, then we can also add infinity if you want to, so that it is compact to write down, but otherwise I have to distinguish which things land in the boundary. So over those 2 points, the coordinates can be 0. Fantastic. What do you think about this set? What I think about this set is that this set is too big. I mean, the map is explicit. We know the points are points with coordinates like this. Okay, I made a choice, but still to be in the image, this A and B must both be squares. And here I'm not saying squares. I'm saying periodic valuation is 0 or at least 2. So a cube is perfectly fine inside this set, right? So it is already constraining which points can come from points from above, but it is not sharp. And actually, we can do better with geometry than just this. So the next step is to see what can we do better with geometry. So this is the other theorem that we prove. And this is following ideas of Abramovich, who introduced this in some paper and then didn't give a proof, say you can do this. And then we wrote a paper about it. So the setting is similar. R is a Dedekind ring, K is the fraction field, but now I'm going to ask that the K is of characteristic 0. And this is because of the tools that we use. And you will see immediately in the first step. So X to Y is again the proper surjective. And then X and Y are proper and integral over K. You can think of your favorite morphism and not so much about the actual requirements that we have here. And yes, the generic fiber should also be reduced. And then the first thing that one can do when one has such a morphism is to, well, go to Abramovich and say, what do I do with this morphism? And say, well, you should find a good toroidal model of this. So what we get is a projective birational map from other varieties that are toroidal embeddings. I'm not going to say what that is, but it is some generalization of the idea of toric variety. With the toroidal map, which somehow carries a lot of structure that we're going to be able to use. And birational here, you probably know, but it means that over some open subset of Y, it's isomorphic to an open subset of Y prime under this map, and the same for X's. So generically, these varieties are the same. We are just changing outside of an open set, and we're making the boundary look nice. So this is something that is already known. I mean, we didn't prove this. So this is a big work about weak toroidalization of a non-closed field by Abramovich, Denef, and Caro. 2013, I think, and so on. And they use characteristic 0, so it's one of the first steps. So of course, you could start from here and then skip this step, but we use characteristic 0 also later. And it is nice to know that you can do this no matter which morphism you start from, and you can find a good model. I wish I knew how to find a good model explicitly, like construct it actually, but that's a different story, perhaps in the future. And then what happens is that these toroidal morphisms are actually log smooth in the sense of log geometry. So they have on the boundary is going to give me a log structure, and this log structure has the nicest possible properties that I can ask for in log geometry. And so this is the thing about this morphism that we are using to prove the result. The result is about how to lift points. How do we do this? So first we find a finite set of places such that we can extend f prime to integral models that are also log smooth, and the map is also log smooth. So we can extend it nicely. And if we sort of a finite set of places, we can do this. So G is log smooth for the closure of the boundaries. X prime, Y prime are all proper and also log smooth where RS. I'm not going to write down everything. And what happens is that with this model, a point beta in Y prime of RS which is also the same of y prime of k. We're still working in the model. Lives. So if it is not in the boundary, given by this toroidalness or given by this log-smooth map, then a point that is not in the boundary lives to x prime, not directly, up to taking an entire cover of the base Rs. There's some arithmetic obstruction that we should always expect to possibly be there, and we have to allow for that. So we can really prescribe the direct lifts as a k point here, but the lifts to x prime et al. Locally over Rs, if and only if certain combinatorial things are satisfied. The firmament of the point beta is contained inside the firmament of the morphism G. And then you ask me, what is this firmament? I never heard of it. So the first person to come up with this was Abramovich. And I'm going to just give a very brief definition. And if you want to know more, you can ask me later. So what is this? I'm going to tell you what it is for G, and then similarly for beta, but you have to specify the log structure. But for G, it's clear that we have a toroidal boundary coming from x prime, y prime is here, gives the log structure. All right, so gamma G is the image of the map of complexes given by the log-smooth map. So we have combinatorial objects attached to our logarithmic maps, these called complexes. If my varieties were toric, then this complexity would be just the fan. So if you know about toric geometry, it's not too scary, and otherwise it is whatever it is the right generalization of that in the for log schemes. And so we just look at this. I use primes, yes. And we look at the lattice points inside these, and we look at the image of this, and then this is what we call the firmament. We don't have time. Yes, and I can tell you that in the application of the example, the one thing that happens is that if we now look at this condition instead of the previous condition, it always gives a subset of this set here, and it gives exactly the image in our case. Yes, I can stop here.